Okay, welcome to the class. Today we're going to have a look at the third lesson of chapter 4. Today's topics are elastic potential energy and simple harmonic motion, and spring and conservation of energy. So considering jumping on a trampoline is fun, right? But is it also work? Each time the students, as shown here in this figure, moves downward, she has to bend her knees and push hard against the trampoline. According to Newton's third law of motion, the trampoline also exerts an equal force in the opposite direction, pushing her upward. So what type of energy does a student jumping on the trampoline have? You know that she has gravitational potential energy relative to the ground when she's in the air above the trampoline. She also has kinetic energy because she's moving. Does she has another type of energy? As the girl pushes down on the trampoline, she stretches the elastic fabric and springs of the trampoline. The downward force of her feet does not work on the trampoline, the downward force of her feet does work on the trampoline, transferring energy to it. This energy temporarily becomes stored energy in the fabric and springs. We will explore the nature of this type of stored energy in this lesson. Okay, so one important type of potential energy is associated with springs and other elastic objects. You are probably familiar with a simple spring, such as the tight coil of wire shown here in this figure 2. In its relaxed state, with no force applied to its end, the spring is at rest, as shown here in figure 2a. Now suppose we pull on the spring with a force F pull, causing the spring to stretch to the right, as shown here in figure 2b. When stretched, the spring exerts a force F spring to the left. Likewise, if we push on the spring with a force F push, it compresses to the position shown in figure 2c. When compressed, the spring exerts a force F spring to the right. In both cases, F spring is called the restorative force because it tends to restore the spring to its nature length. So the amount of force exerted by a spring is proportional to the spring's displacement. This is called Hooke's law, named after Robert Hooke, who discovered the relationship in 1678. Hooke's law has a force exerted by the spring is given by the following formula here. Well, in this equation, Fx is the force exerted by the spring on whatever stretches it, and delta x is the displacement of the spring from its unstretched equilibrium position. The constant of proportionality K is called the spring constant of the spring, and it corresponds to the stiffness of the spring. Springs that are stiff have a larger value for K and require a large force to extend or compress them. Springs that stretch easily have smaller values of K. An essential feature of Hooke's law is that direction of the spring force is opposite to the direction of the displacement from the equilibrium. If delta x is upward, then Fx is downward. Whereas if delta x is downward, then Fx is upward. Okay, so careful with this equation here. Fx is a vector. Delta x is also a vector. The direction of these two vectors are opposite. So a spring that obeys Hooke's law exactly is called an ideal spring, and no internal or external friction acts on it. Although we have only discussed springs so far, Hooke's law applies to many elastic devices. So now let's consider a sample problem in tutorial 1, in which we'll use Hooke's law to predict the effect of an applied force on a spring. Okay, so the following sample problem examines how to determine the spring constant of spring and how to use the spring constant to predict the stretch of the spring while a mass is attached to it. Okay, let's consider a sample problem here. So a spring hangs at rest from a support. If you suspend a 0.46 kilogram mass from the spring, its deflection is 7.9 centimeters, which is shown here in figure 4. So there are 4 questions. A, can you determine the spring constant according to the formula we have just learned? Question B, can you calculate the displacement in centimeters of the same spring when a 0.75 kilogram mass hangs from it instead? Question C, suppose 0.75 kilogram mass is pushed upward so that it rises past the spring's unstretched position, compressing the spring. Can you calculate the net force on the mass when the spring is compressed 0.3 centimeters? Include a free body diagram in your solution. And question D, can you determine the acceleration of the mass at the position given in question C once it is released? Okay, I'll give you 10 minutes to consider this problem. Well, probably want to refer to the formula we have just learned here. The formula that demonstrates the Hooke's law, okay? You need to write this down to your notebook first. Okay, you can start, and after that, we'll have a look at the solution together. All right, have we finished? Okay, let's have a look at the solution together. So first, let's have a look at question A. Okay, so the force of gravity on the mass points down, right? So the on the other hand, the restorative spring force on the mass points up because the spring is stretched down. To calculate the total force, subtract the magnitudes. First of all, Fg equals mg, direction is down. Or you can rewrite this to negative mg with direction up. Fx, which is the restorative force in the spring, equals negative k delta x, which is k times delta x, direction is up. Since the mass is not accelerating, we have the net force equals 0. According to Newton's second law, we have net force sigma F equals 0, which is k delta x minus mg equals 0. Therefore, k equals mg over delta x. And then put all the values in, we have k equals 57.1 newtons per meter. Therefore, the spring constant is 57 newtons per meter. Any questions? No? Okay, then let's have a look at question B. The force of gravity on the mass points down, right? The spring force on the mass points up because the spring is displaced down. So gravity Fg equals mg. Direction is down, or you can also rewrite this to negative mg if you choose up as the positive direction. Again, Fx equals negative k delta x, or kx, direction is up. Since the mass is not accelerating, again, we have net force equals 0. So that gives us kx minus mg equals 0, and that delta x equals mg over k, which is about 0.13 meters. Any questions? So the displacement of the spring is 13 centimeters. Direction is down. Okay, question C. Okay, first of all, we can draw a free body diagram for the mass, which is shown here in figure 5. Then the force of gravity on mass points down. The spring force on the mass points down because the spring is compressed upward. So Fg equals mg down, Fx equals kx down. Then F net equals Fg plus Fx. Note here the direction is down. Therefore, the net force is 10.4 newtons. Direction is down. So the net force is 10 newtons down when the spring has been compressed by 0.053 meters. Okay, so question D. According to Newton's second law, we have F net force equals ma, and A equals F net over m, right? Net force is 10.4 newtons. The mass is 0.75 kilograms, so the acceleration is about 14 meters per square second. Direction is down. When the spring is compressed, 0.053 meters. If the mass is moving upwards, the downward acceleration means that it is slowing down due to the force of gravity and the elastic force of the spring. Okay, any questions? All right, next let's have a look at concept of elastic potential energy. So the spring jumping on the trampoline in figure 1, which we have seen here, does work on the trampoline every time she pushes down on it, right? As a student comes down for a jump and hits the trampoline surface, she has kinetic energy. As the trampoline fabric and the springs stretch, she transfers her kinetic energy into potential energy stored in the trampoline. Energy that is stored in objects that are compressed or stretched is called elastic potential energy. This stored energy in the trampoline can be transferred back to the student, giving her kinetic energy and she needs for her next upward jump. Unlike gravitational potential energy, elastic potential energy does not depend on an object elevation. Instead, it depends on the amount of compression or stretching. To determine the potential energy, we can calculate the change in kinetic energy of a mass attached to a spring as the spring is compressed or stretched. The change in kinetic energy equals the work done by the spring force. The work done by the spring force can be determined from a graph of applied force versus displacement. The area under a force displacement graph for an ideal spring has a shape of triangle. The area of this triangle equals the work done on the spring by the applied force. This applied force is equal but opposite to the spring force on an attached object. Therefore, the work done on the spring to displace it will equal the negative the work done by the spring on the object as it is displaced, which is shown here in this figure, figure 6. This figure shows a graph of a spring force on a mass attached to the spring as the spring is stretched or compressed. The slope of this line equals negative k, following Hooke's law. The direction of the spring force is always opposite to the displacement. We can interpret the area between F versus X line and the x-axis for a given X value as the total work done on the spring as the spring stretches or compresses by delta X. The work is negative of the total work done by the spring. Any questions? So since the area of a triangle equals 1/2 the base length times height, the work W done on the spring with a spring constant K can be given by this formula here. W equals 1/2 times delta X times K delta X. Therefore, we have W equals 1/2 times K times delta X squared. So basically this means the work done by the spring force is the negative of this amount and is also the negative of the change in potential energy. This means that the work done stretching or compressing the spring is transformed into elastic potential energy. Remember that work is a scalar quantity and thus directions can be ignored. We can equivalently write the equation as the following. So be careful with this formula here. I think you should write this down to notebook. E, which means the elastic potential energy, can be calculated by this formula, 1/2 times K times delta X squared, okay? Where E is a elastic potential energy. As with all types of energy, elastic potential energy can be transformed to kinetic energy or to other forms of potential energy. When the student jumps on the trampoline, some of the energy transforms into kinetic energy and gravitational potential energy. Some also transforms into vibrational energy of the trampoline, sound energy, and thermal energy. Okay, so please write this down onto a notebook and we'll use this formula to solve the following sample problems. Okay, so now let's consider this sample problem here. A 42-kilogram teenager balances briefly on a pogo stick, causing the spring in the stick to compress downward by 0.18 meters. Can you determine the elastic potential energy of the teenager? Okay, I'll give you 5 minutes to have a look at this question, and after that, we'll have a look at solution together. Okay, let's have a look at the solution. Okay, so in this question, the force of gravity on the teenager points down, right? The spring force on the teenager points up because the spring is compressed down. So in order to find the elastic potential energy, remember we can use a formula E equals 1/2 times K times delta X squared, right? So first of all, you need to find K. So we can use this relationship here, Fg equals mg down, Fx equals negative K delta X. Then Fx equals Kx up, right? Since the teenager is not accelerating, net force on it should be 0. Therefore, we have K delta X up equals mg down. Therefore, that gives us K equals mg over delta X. So be careful with the direction of each vector here. In one-dimensional space, we use either positive or negative signs to indicate the direction of a vector, right? So K equals mg over delta X. Then put all the values in. We have K is approximately 2.29 times 10 cube newtons per square meter. Then use the spring constant to determine the elastic potential energy. EE equals 1/2 times K times delta X squared, which is about 37 joules. So the teenager on the pogo stick has 37 joules of elastic potential energy. Do you have any questions? Okay, if no questions, let's have a look at another type of motion, which is called periodic motion. It is shown here in this diagram, in this graph. A person usually jumps more than one time on the trampoline or pogo stick. Often a person will jump up and down over and over again. The motion usually changes slightly with each jump. But suppose a jumper has a regular motion so that the height and time for each jump are always the same. Motion that repeats in this way is called periodic motion. Okay, so one of the periodic motion is called simple harmonic motion. So suppose a block is connected to the spring and both are resting on a frictionless surface. The block is at equilibrium when it's resting at the initial position x equals 0, as shown here in figure 7a. In figure 7b, then the spring is stretched to its maximum limit or amplitude a. Displacement is then x equals positive a, right? Is maximized and the block stops momentarily. The block's motion is then reversed as the spring pulls it back towards the equilibrium point, which is illustrated by figure 7c. Then the block continues to move past the equilibrium point and stops when the spring is fully compressed. And negative displacement, x equals negative a, is maximized, which is shown here in figure 7d. The restorative force of the spring moves the system towards equilibrium and the cycle continues. Notice that the force exerted by the spring is not constant. As the spring approaches its equilibrium point, the displacement delta x decreases. Since Fx is proportional to the magnitude of this displacement, Fx also decreases during this time. The mass in figure 7 here will continue to move right and left between A and negative A if both the spring and surface are frictionless, which is shown here in the graph on the top, right? The back and forth motion is an example of simple harmonic motion. Simple harmonic motion, which is always often abbreviated as SHM, is a back and forth or periodic. Periodic motion in which the moving object experiences a force that is proportional and opposite to the displacement. An object undergoing SHM is often referred to as a simple harmonic oscillator. Well, you can visualize back and forth motions that is similar to SHM by thinking about a tennis ball hit from one side of the net to the other over and over again. If the players stand still in the same positions and if they apply the same force to the ball with each hit, the ball will continually have the same back and forth motion, right? Okay, so when describing the simple harmonic motion mathematically, we can picture a reference circle like the CD shown here in figure 8, which is at the bottom of this page. The mass attached to the spring in this figure vibrates left and right with the simple harmonic motion. At the same time, the point shown on the CD rotates with uniform circular motion. Suppose that the amplitude of the SHM equals the reference point's radius of revolution. What if the period of vibration for SHM exactly equals the period of rotation for the CD? Then the x-coordinates of the mass and the point on the CD will remain equal at all times, right? This means that acceleration of the mass is the same as acceleration of the x-coordinate of the reference point at all times. So when the reference point and the mass are at point of maximum stretch in the spring, the centripetal acceleration of the reference point AC is directed towards negative x. The acceleration of x coordinate at this moment is AC. So the acceleration of the mass at this moment is also AC. This fact will allow us to calculate the period of motion of the mass. So for an object with radius r in uniform circular motion with period t, the centripetal acceleration is given by A subscript C equals 4 pi square r over t square, right? This is what we have learned in previous lessons. Then we can rewrite this equation to solve for t. T square equals 4 pi square r over AC, right? Which means t equals 2 pi times square root of r over AC. So we can apply this result to the simple harmonic motion. We can let r equals a, which is the amplitude for the reference circle. We then have the period of the simple harmonic motion, t equals 2 pi over a times square root of a over AC. Next, we can use Hooke's law and Newton's second law to calculate acceleration of the mass. The equation fx equals negative kx equals max means that acceleration ax equals negative kx over m. The ratio of the magnitude of displacement to the magnitude of the acceleration is then given by delta x here over ax equals m over k. At the point of maximum stretch, we have delta x over ax equals a over acceleration ac, which means m over k equals a over c, right? So if you substitute this result into the equation for the period, we then obtain the equation of the period of a mass on a spring, which is here. So this is a formula we can use to find the period of a simple harmonic motion. T equals 2 pi over 2 pi times square root of m over k. The period t of a SHM is the amount of time for one cycle of a motion. Period is measured in seconds. The inverse of t equals the number of cycles per second, or the frequency denoted by f. The units of frequency are called hertz, and 1 hertz equals 1 cycle per second. You have any questions? Amplitude. Okay, I think you should write this down, and we're going to have a look at a sample problem which illustrates how we can use this formula to solve similar questions. Okay, in this formula, M is a mass, and K is called the spring constant. Okay, then you don't have any questions. Let's consider this question here. When the diving board bends, the restoring force due to the board elastic properties obeys Hooke's laws for an elastic material. Suppose a diver of mass 85 kilograms stands on the diving board with spring constant 8.1 times 10 cube newtons per meter. The mass of the board is much smaller than diver's mass. Calculate the period and frequency at which the board vibrates. Okay, I'll give you 5 minutes to have a look at this question by yourself. Okay, any ideas? We have just learned this formula, right? For a simple harmonic motion, the period can be given by 2 pi times square root of m over k. So do you have these quantities in this question? You have k and m, right? So we can directly plug these values into this formula to find the period for this harmonic motion. Okay, let's have a look at the solution here. So we can use equations for simple harmonic motion. The period t equals 2 pi times square root of m over k. And also note that frequency equals the reciprocal of t. So first of all, we can solve t. T is 2 pi times 85 kilograms over 8.1 times 10 cube newtons per meter, which is about 0.64 seconds. and F is reciprocal of T, which is about 1.6 Hertz. So the diving board will vibrate with a period with a period of about 0.64 second and a frequency of 1.6 Hertz. All right, notice that the calculations in this sample problem did not require you to identify how far the diving board bends. The period and frequency depend only on the mass that exerts the force and the spring constant of the elastic material. Well, you can actually identify numerous examples of the simple harmonic motion in our everyday life. If you ignore friction, for example, a child on the playground swing may spin back and forth at a regular rate. Springs on guitars and violins vibrate when plunked. The planets move in periodic orbits around the sun. Automobiles use springs to provide a cushion effect. Also, you do not experience long periods of SHM when riding in car because shock observers provide friction on the springs. We will explore this behavior of shock observers further in our next few lessons. All right, now you can take a 5 minutes break and please return before 20 past 10. We'll have a look at the second half of this lesson, springs and conservation of energy. All right, welcome back to the classroom. So now let's dive into the second half of this lesson. We're going to have a look at springs and the conservation of energy. Most drivers try to avoid collisions, but not at a demolition derby like the one shown here in this figure. The point of demolition derby is to crash your car into as many other cars as possible. Each car tries to damage the other cars so much that they will stop working. The harder the crash, the more damage you are likely to do. The last car running is the winner. So how can drivers of demolition cars avoid serious injury? What types of safety equipment do they use? Like most drivers, they wear seatbelts to hold themselves securely in their seat. They have shoulder straps to prevent lurching forward. Padding inside the driver's side door might provide cushioning from side impacts. Most cars on the road, however, have safety features that are missing or unimportant in demolition cars. Cars you ride in probably have airbags to cushion the passengers during a crash. They might have anti-lock brakes or other computer control systems that act during emergency situations. In this section, we will explore the physics behind safety equipment and other systems in which energy is stored and transferred. Okay, now let's have a look at the concept of conservation of mechanical energy. Systems that make a car safe use either springs or elastic materials. So they have elastic potential energy. You have already learned about conservation of energy in an isolated system, right? We have talked about this in our previous lesson. The law of conservation of energy includes elastic potential energy as well. Energy is neither created nor destroyed in an isolated system, but it can be transformed between kinetic energy, gravitational potential energy, elastic potential energy, and other forms of energy. In this section, we'll explore interactions of systems in which mechanical energy is conserved. That is, the total amount of kinetic, gravitational potential, and elastic potential energy remains constant. Energy losses due to effects such as friction, air resistance, thermal energy, and sound can be ignored as negligible. So suppose, for example, a student jumps up from a diving board, assuming air friction is negligible, the mechanical energy of the diver will be conserved. Use the diving board as a reference point, y equals 0, for measuring the gravitational potential energy. At the maximum height h above the diving board, the diver has only gravitational potential energy equal to mg delta y, right? He then starts to fall toward the board, gaining kinetic energy because of his motion. The diver's distance above the reference point is decreasing, so his gravitational potential energy is decreasing as well. His total mechanical energy does not change. Halfway to the board, his gravitational potential energy has decreased by half. So it exactly equals his kinetic energy. At the moment just before the diver hit the diving board, the gravitational potential energy is 0. And he has kinetic energy that equals his starting gravitational potential energy. Conservation of mechanical energy still applies after the diver hits the diving board. He applies a downward force on the board, displacing it a distance x. This work transfers the diver's kinetic energy to the board. The energy is stored in the board as elastic potential energy, and the board dips down. The diver drops below y equals 0, so his gravitational potential energy becomes negative. the total elastic potential energy increases to offset the decrease in gravitational potential energy. In reality, some energy is lost as friction, sound, and vibrations of the diving board. If we ignore these effects, mechanical energy is conserved. We will apply the conservation of mechanical energy in the following tutorial. Okay, so now let's consider tutorial 1 here. In which we'll analyze the transformations of gravitational potential, kinetic, and elastic potential energies of various systems. So let's consider sample problem 1 here, analyzing energy transformations. In this problem, you will model collision and apply conservation of energy to analyze the outcome. So here, a model car of mass of 5.0 kilograms slides down a frictionless ramp into a spring with spring constant K equals 4.9 K newtons per meter, as shown here in figure 2. So first, the spring experienced a maximum compression of 22 centimeters. Can you determine the height of the initial release point? Second, calculate the speed of the model car when the spring has been compressed 15 centimeters. C, determine the maximum acceleration of the car after it hits the spring. Okay, I'll give you 10 minutes to consider this problem by yourself, and after that, we'll have a look at the solution together. You can start now. Okay, have you finished? Okay, let's have a look at solutions one by one. First, question A. Since energy is conserved, the change in potential energy of the model car must equal the change in elastic potential energy when the spring is compressed, right? So if we choose the bottom of the ramp to the y equals 0 reference point, the car will have no gravitational potential energy at the bottom of the ramp. The initial gravitational potential energy has been converted to kinetic energy. When the spring is fully compressed, the kinetic energy has been converted to elastic potential energy. Therefore, the spring's initial gravitational potential energy must equal its final elastic potential energy, which is Eg equals EE. That gives us mg delta y equals 1/2 times k times delta x squared. Therefore, delta y equals k times delta x squared over 2mg. We know all the values for these quantities, right? Delta y is approximately 2.42 meters. So the initial height of the model car is 2.4 meters, approximately. Okay, next, let's consider question B. Since energy is conserved, the sum of the kinetic energy and the elastic potential energy when the spring is compressed must equal the initial gravitational potential energy of the car. The initial gravitational potential energy is given by Eg equals mg delta y, which is 119 joules. When the spring is compressed to delta x equals 15 centimeters, then the elastic potential energy can be given by E elastic equals 1/2 times k times delta x squared, right? So that is about 50.1 joules. So the kinetic energy when x equals 15 centimeters must equal the difference between the initial gravitational potential energy of the car and the final elastic potential energy of the spring, which is the difference between 119 joules and 55.1 joules, which is about 63.9 joules. Finally, use EK to solve for V. We have 1/2 times mv squared equals EK. Therefore, V squared equals 2EK over m. And V equals the positive square root of 2EK over m, which is around 5.1 meters per second. Therefore, the speed of the model car when the spring is compressed 15 centimeters is 5.1 meters per second. Any questions? Okay, so in question C, the maximum acceleration occurs once the maximum force is acting, right? And this occurs when the spring is at the maximum compression of 22 centimeters. So we can combine Hooke's law and Newton's second law. This gives us net force exerted on the model car equals Fx, which is provided solely by the spring's force, which gives us ma equals negative k delta x. Therefore, the acceleration is k delta x over negative m, which is about 2.2 times 10 square meters per second. And the direction should be towards the ramp, right? So the maximum acceleration of the model car is 2.2 times 10 square meters per square second, directed towards the ramp. All right, have a look at this question. Do you have any questions? No? Okay, then let's consider another sample problem here. Okay, this time we have a 48-kilogram child bounces on a pogo stick. At the lowest point of the bounce, the compressed spring in the stick has 120 joules of elastic potential energy. as it compresses 0.19 meters. Assume that the pogo stick is light enough that we can ignore its mass. A determines the child maximum height during the jump following the bounce. B determines the child maximum speed during the jump. Okay, I'll give you 5 minutes to consider this question here. And after that, we'll have a look at the solution together. All right, any ideas? Okay, let's have a look at the solution here. So we can choose the lowest point of the bounce as y equals 0 at first point. At the maximum height delta y, all elastic potential energy has converted to gravitational potential energy, right? So we have the following relationship: Eg equals EE, mg delta y equals E elastic. Then delta y should be elastic potential energy over mg. And this gives us about 0.26 meters. So the child rises 0.26 meter from the lowest point of the bounce. That concludes question A. For question B, the point of the maximum speed is the point at which a spring is at its equilibrium position, right? At this position, all of the elastic potential energy has been converted to gravitational potential energy and kinetic energy. If we choose the lowest part of the bounce at the y equals 0 reference point, then the equilibrium position, we have E gravitational potential energy equals mg delta y. So that gives us 89.4 joules. The kinetic energy is the difference between the initial elastic potential energy and gravitational potential energy, which gives us EK equals 120 joules minus 89.4 joules, which is 30.6 joules. Now we can solve for V, which is 1/2 mv squared equals EK. Then V is about 1.1 meters per second. So the child maximum speed is 1.1 meters per second. All right, any questions? Okay, no questions. Let's consider another. Okay, this is a solution for question B. You can have a look at that. Any questions, just let me know, okay? All right, any thoughts on this? Sample problem 3. There are 3 questions. Block with a mass of 2 kilograms is held against the spring with spring constant 250 newtons per meter. The block compresses the spring 22 centimeters from its equilibrium position. After the block is released, it travels along a frictionless surface and then up a frictionless ramp. The ramp's angle of inclination is 30 degrees. Okay, let's have a look at the first question. Determine the elastic potential energy stored in the spring before the mass is released. This is straightforward, right? You know, K is 250 kilograms per. Sorry, we know K here is 250 Newton per meter. X is 22 centimeters, which is 0.22 meters, right? And we want to find the elastic potential energy E. Before the block is released, the entire mechanical energy of the block spring system is in the form of elastic potential energy stored in the compressed spring. We can use the given information to determine the amount of stored energy, E elastic, which is given by this formula, 1/2 times K times delta X squared. Then put all the values in. K is 250 newtons per meter and X is 0.22 meters. So the elastic potential energy is 6.05 joules, which is approximately 6.0 joules. For second question, as the block travels along the flat surface, all of the elastic potential energy is converted to kinetic energy. We can use this to determine the speed of the block using the equation. Kinetic energy E equals 1/2 times m times v squared. So v is square root of 2e over m, which is approximately 2.46 meters per second. So the block will travel at a constant speed of 2.5 meters per second along the frictionless horizontal surface. Okay, next question C. As the block travels up the ramp, kinetic energy is gradually converted to gravitational potential energy. When the block reaches its maximum height, all energy will be in potential form. Use this to determine the vertical height attained, delta y, and then use trigonometry to calculate the distance traveled along the ramp, d, as shown here in figure 3. Okay, first of all, the gravitational potential energy is mg delta y. Also, we have delta y over d is sine theta, right? So mechanical energy is conserved throughout this problem because there are no energy losses due to friction. The total potential energy at the top of the block's path is therefore 6.05 joules. Then we can have delta y is Eg, which is gravitational potential energy over mg, which is given by 0.308 meters. So now we can use sine ratio to determine how far along the ramp the block travels. Delta y over d equals sine theta. That means delta y equals d times sine theta. So d equals delta y over sine theta, which is 0.62 meters. So the block will travel a distance of 0.62 meters or 62 centimeters along the ramp. Okay, any questions? All right, if no questions, let's have a look at another concept, which is called perpetual motion machines. An ideal spring would never lose energy and would continue with SHM forever, or as long as you did not disturb it. A machine that can continue to operate for an unlimited amount of time without outside help is a perpetual motion machine. To be a true perpetual motion machine, the machine must be able to run forever without restarting or refueling. A grandfather clock, for example, is not a perpetual motion machine, since you must wind it up every now and then. So as shown here in this figure, figure 4, which shows a device called Newton's cradle. The leftmost ball has gravitational potential energy with respect to other balls. Once released, the ball will interact with the other balls in such a way as to imitate perpetual motion. You will have the opportunity to explore the physics behind Newton's cradle in chapter 5, which we'll discuss later. So an ideal version of Newton's cradle would never lose energy, and the cycle of falling, gliding, and rising would continue forever. It would then be a perpetual motion machine. So the question is, can we build such a machine? Well, actually, the answer is no. In real-world machines, some mechanical energy will always be lost from the system as thermal energy, sound energy, or other forms of energy. This loss of energy can be useful. For example, the purpose of shock absorbers in cars, which we mention in the next section, is to use friction to stop the SHM, simple harmonic motion, of the car's spring. Okay, so let's have a look at the related concept, which is called damped harmonic motion. So far we have ignored the effect of friction on the motion of simple harmonic motion, right? The friction in a real periodic system is referred to as damping, and the harmonic motion of a system affected by friction is called damped harmonic motion. Presence of friction means that the mechanical energy of the system will be transformed into thermal energy, and the system's motion will not continue perpetually. We can classify damped motion into 3 broad categories, which are underdamped, overdamped, and critically damped, which are shown here in this figure on the left. So consider a pendulum. Curve 3 here in this figure shows how the displacement varies with time when the damping is weak. That means when there is only a small amount of friction. This curve applies to any weakly damped harmonic oscillator. It describes a back and forth swing of a pendulum or the motion of a mass attached to a spring on a horizontal surface when the surface is quite slippery. The system still oscillates because the displacement alternates between positive and negative values, but the amplitude of the oscillation gradually decreases with time. The amplitude eventually goes to 0, but the system undergoes many oscillations before damping brings it to rest. This type of motion is an underdamped oscillation. When quite a bit of friction exists, the oscillator is overdamped. The resulting displacement as a function of time in this case is shown here as curve 1 in this figure. This type of motion happens when the mass moves through a very thick fluid, like the hydraulic fluid inside the closing mechanisms on many doors. If you put a mass of an overdamped oscillator to one side and then release it, the mass moves extremely slowly back to the equilibrium. Critically damped motion falls in between the two extreme cases. In underdamped motion, displacement always passes through 0. The equilibrium point at least once, and usually many times, before the system comes to rest. In contrast, an overdamped system released from the rest moves just to the equilibrium point, but not beyond. In critically damped motion, displacement falls to 0 as quickly as possible without moving past the equilibrium position. Displacement as a function of time for the critically damped case is illustrated by curve 2 in this figure on the left. So get yourself familiar with 3 types of damped harmonic motion according to this graph, okay? Overdamped, which is shown here in the black curve, critically damped, which is shown here in the red curve, and the underdamped, which is shown here in the green curve. So these different categories of damping have different applications. For example, a car's shock absorbers provide damping for springs that support the car's body, which is shown here in figure 6 on the right. Shock absorbers enable the tires to move up and down over bumps in the road without directly passing vibrations to the car's body or passengers. When the car hit a bump, the springs compress to make the ride as comfortable as possible. The shock absorbers critically damp the motion of the springs. The critically damped motion means the body of the car returns to its original height as quickly as possible. Worn out shock absorbers lead to underdamped motion, and the car bounces up and down more. Overdamped shock absorbers give a soft, spongy ride with poor steering response and handling. Okay, so that's the end of today's class. And please remember to complete your homework and submit before the deadline, okay? I'll see you next time.